So something I feel like I kind of forgot to talk about last or any class really is kind of how to find the formula for a sequence given just like a list of the first like five or six terms. So I feel like we should do a few examples like that, and then we will probably also talk about some recursive sequences because I kind of didn't do that either. So let's say we're given something like the follow. Oh, I should write some things down here. It's Co-21C. It's the first day of October. And we're going to do some finding the formula for a sequence. So sometimes it's not too terrible. Sometimes it's really terrible. Let's look at some examples. Sure, let's look at this first example, like 7 over 5, comma, negative 11 over 25, 15 over 125, negative 19 over 625, etc. So a couple things I'll say. Usually when it's a fraction, not always, but usually, the bottom and the top are kind of completely separate from each other. Like they have nothing to do with each other, really. You're kind of tasked with finding a formula for what's going on in the numerator and formula for what's going on in the denominator. And this is certainly the case here. And I would actually say there's often kind of three components or two components. Here there's three because it's also alternating. So we're going to think of this as our a sub 1, this is our a sub 2, a sub 3, etc. So let's deal with the top first. And I'm going to deal with it in a non-alternating fashion. So if I look at 7, 11, 15, 19, I see that those terms are increasing by the same amount each time. That's right. I'm increasing by 4, by 4, by 4. So I'm pretty sure the formula for the top part of this is going to be 4 times n plus or minus something. So the top part, we're going to need a 4n. And here's what we're going to do. If I actually started with n equal to 1, which is where I usually would choose to start, maybe 0, but usually 1. By playing n equal to 1, 4 times 1 is 4. But I want to start with 7. So how do I get from 4 to 7? I add 3. So that's going to be my actual formula for the top part, 4n plus 3. And I'll check. If n is 1, I get 7. If n is 2, I get 8 plus 3, which is 11. If n is 3, I get 12 plus 3, which is 15. It looks like it's working out just fine. So in general, if you're increasing by the same amount each time, you need that number multiplied by n. Because n is increasing by how much each time? 1. So if I want to increase by 4 every time, and n is increasing by 1 every time, I need to multiply n by 4 to increase by 4 every time. The bottom, however, is not the same, right? We're not increasing by the same amount each time, but you might recognize those as just powers of 5. You might also recognize that on the bottom, for, say, our 5 and our 25 and our 125 and our 625, we are multiplying by the same amount each time. In other words, that bottom part is a geometric sequence where we are multiplying by the same ratio every time. We're multiplying by 5, by 5, by 5. You might also just notice that it's 5 to the first, 5 to the second, 5 to the third, and 5 to the fourth. So it looks like our bottom formula is probably going to be 5 to the n. Or in general, kind of in general, whatever thing you're multiplying by, that's going to be raised to the nth power. So you're multiplying by 5 every time, you're going to get 5 to the n. There's a little bit more to say there, depending on if we have something that's not just a nice power of 5, but we'll get there in a minute. And then we have this alternating sign part, which is easy to deal with. So if it's alternating, it's going to be one of two things typically. It's either going to be negative 1 to the n or negative 1 to the n plus 1. And you just have to decide which one it is based on if you want to start negative or positive. So if we're starting with n equal to 1, negative 1 to the 1 would start off negative. Negative 1 to the 1 plus 1 would start off positive, and we want to start off positive. So this is the one we need in this situation if we're starting at n equals 1. So it looks like here, the formula for our sequence is negative 1 to the n plus 1 times 4n plus 3 on top and 5 to the n on the bottom. Yeah, we'll get there in a minute. Okay. So let's look at a couple more. Yeah, a few more. So let's say we had something like the following. Yeah. 5, 4, 3, 4, 5, 4, 3, 4, 5, and so on and so on and so on. Which in my opinion is one of the more annoying examples. If you know what to do, it's easy. If you don't know what to do, it's not. I know that sounds like the dumbest thing, right? Obviously, if you know how to do it, it's easy. If you don't know how to do it, it's hard. But like this one, there's a pattern that you're aware of that you might not know you're aware of. So here's what I would suggest. If you have something that's kind of starting somewhere and then going down, down, up, down, up, down, up. To me, it kind of looks like a sinusoidal function, like cosine or sine. Like the peaks, the middles, and the valleys of a sine or a cosine. So it might be easier to see this as 4 plus 1, 4 plus 0, 4 minus 1, 4 plus 0, 4 plus 1, and so on and so on and so on. So I'm looking for something that really, I don't care about the 4, but I want something that's hitting 1, then 0, then negative 1, then 0, then 1, then 0, then negative 1, then 0. And to me, I'm thinking of that as the four corners of the unit circle, the cosine value. I'm thinking cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, cosine of 3 pi over 2 is 0. 1, 0, negative 1, 0. 1, 0, negative 1, 0. So what I want here is and again, if I'm starting at, so here, this is interesting. Here's where I'm going to choose to start at n equals 0. So starting at n equals 0, we'll do it both ways. We want our a sub n to equal 4 plus cosine of pi times n over 2. If you plug in n equals 0, you get cosine of 0, which is 1. Plug in n equals 1, you get cosine of pi over 2, which is 0. Plug in n equals 2, you get cosine of pi, which is negative 1, and so on. This is going to move you 90 degrees every time, so you're going to get to the next nice value. As is typical, there's actually like a bajillion ways you could actually write this. Another equally, I hesitate to say equally here. You could also start at n equals 1, either a terrible way or a nice way. Here's the terrible way. You could say, well, I just want to make this one smaller, so it's going to be cosine of pi times n minus 1 over 2. That'll still do the same thing for you. But there's a nicer way to do it. If you have to start at n equals 1, use the sign values. If you start at n equals 1, sine of pi over 2 is 1, and then 0, and then negative 1, and then 0. So you could also write this as a sub n is 4 plus sine of pi times n over 2. And that would also work just fine. But if you see this kind of pattern where you're going down, up, down, up, down, it often means someone has used a cosine or a sine like this. But that's usually, I'll point out, how do I say this the right way? No, there's not a good way to say it. I don't have a good way to say it. But it leads me to another one, which I kind of came up with, which is kind of funky, but I want to point something out. So here's one that might look easy from the get-go. It is not. 3, 1/3, 1/3, 1/27th, 1/27th, 1 over 243, 1 over 243, etc. Or if you prefer, you can even write it with the powers 3, 1 over 3, 1 over 3, 1 over 3 cubed, 1 over 3 cubed, 1 over 3 to the fifth, 1 over 3 to the fifth. Which kind of doesn't seem terrible, but also does, because like how do you come up with a formula where like the term stays the same for the next term? That's not the point here. That's not actually what we're being asked to do. This example is meant to demonstrate how terrible it is when someone simplifies something for you. I simplified this. I made it harder by simplifying, by reducing all my fractions. If I didn't reduce all my fractions, here's what the pattern actually looks like. If I remember what I wrote in the beginning here. Yeah, we have 3 over 1, 1 over 3, 3 over 9, 1 over 27, 3 over 81, 1 over 3 to the fifth, 3 over 3 to the sixth, etc., etc., etc. So I was disguising a lot here because really the denominator is just subsequent powers of 3, and the numerator is kind of this oscillating thing again. So we actually have totally distinct things to deal with here. So the denominator is not bad. Again, I probably would choose to start at n equals 1. So we start at n equals 1. My denominator, or the bottom, is going to be 3 to the n minus 1. I meant to not give away the formula just at the beginning there, but oh well. I was going to say we have 3 to the 0, and then 3 to the first, and then 3 to the second, and then 3 to the third. So we're starting at n equals 1. We need 3 to the 1 minus 1, 3 to the 2 minus 1. So we need 3 to the n minus 1 for the bottom. The top is a little more interesting. It's this alternating thing, back and forth, back and forth, back and forth, back and forth. Usually that means you're going to want a negative 1 to the n, or a negative 1 to the n plus 1, because that will give you the alternating part, and then you kind of just adjust it. So here, 3, 1, 3, 1, 3, 1, 3, I think I want 2, right? That's the middle of 1 and 3. And then I either want to add 1 or subtract 1. So I want a plus negative 1 to the n. Is that going to be right? Am I going to start? Let's see, if I start at n equals 1, that's going to give me 2 plus negative 1, which is going to be 1 on top. Oh, I want that instead. But that'll alternate back and forth between 1 and 3 and 1 and 3 and 1 and 3. And you can actually make that work for kind of any two numbers you're alternating back and forth between. Let me show you what I mean in a second. So here it looks like our sequence formula would be something like, not something like, it would be exactly like 2 plus negative 1 to the n plus 1, or n minus 1. It actually doesn't matter what you use. If it's negative 1 to the n plus 1 or negative 1 to the n minus 1, it's still going to be negative at the same times and positive at the same times. On the bottom, we have 3 to the n minus 1. Okay. But I said something earlier that I think is worth addressing, which is you can actually do this kind of for any two numbers that alternate back and forth. So someone tell me a number, a nice integer number, positive, any number actually, any integer. 5. Someone else give me another one that's not too close to 5. Not too close to 5. Sure, 9. So let's say we had 5, 9, 5, 9, 5, 9 forever and ever and ever. Here's how you deal with that. So you find the middle. Luckily, the middle is nice and easy. The middle is 7. And then you just add the difference between the middle and either one. So the difference between 7 and 9 and 7 and 5 is 2 times negative 1 to the either n or n plus 1. In this case, I'm going to start at n equals 1. So that's going to work out perfectly. If n is 1, I get 7 minus 2. If n is 2, I get 7 plus 2, 7 minus 2, 7 plus 2, 7 minus 2, 7 plus 2. Totally gives me that. So you can always find a fairly direct way to write something like that. The reason I'm mentioning this is because for Lee's class, the only class I've seen the work for, there's on this quiz of yours, problem 1A definitely is, well, there's a fraction that's unsimplified, and it's for a reason. He's hiding something because he simplified some of the fractions and he didn't simplify some of the other fractions. So that should help with that. I was like, how do you do this one? It looks totally crazy. 2010, 2010. No, it's not 2010. It's 2020. All right. What else did I have to say here? I had other things I want to talk about too. Oh, yeah, sure. So some sequences are nice and explicitly formulaic. Like you can find an explicit function or formula for that sequence for any value of n. But some of them are recursive, meaning you can only find the next value based on the previous value or values plural. Maybe an example of the most famous recursive formula, recursive sequence formula ever is the Fibonacci sequence. So the Fibonacci sequence says, let me make sure I write the numbers the right way. Usually we say the 0th term is, oh, what did we say? I don't know. There's lots of ways to write it. You can start with a 0, and then the first term is a 1, and then every subsequent term, f sub n, is equal to the previous term plus the previous term. Right? That's the Fibonacci sequence. You add the previous two terms to get the next term. So our f sub 2 would be f sub 1 plus f sub 0, which is 1 plus 0, which is 1. And our f sub 3 would be f sub 2 plus f sub 1, which is 1 plus 1, which is 2. And f sub 4 would be 2 plus 1, which is 3, and so on and so on and so on. So that's kind of the gist of a recursive sequence, is you need the previous terms to find the next term. What's kind of neat is that a lot of these recursive sequences actually do have an explicit formula. There's a really wacky explicit formula for the nth term of the Fibonacci sequence. You should look it up sometime. It has to do with the golden ratio. It's kind of neat. It's like 1 plus root 5 over 2 to the nth power plus some other stuff. Feels like you look at it, you're like, how could this ever be an integer, let alone always be an integer? But it is always an integer. So if you have the time, look up the explicit formula for the nth term of the Fibonacci sequence. It's kind of neat. But usually we have something more like, maybe something like, where did I go here? Yeah. Like our terms might be something like 3, and then the square root of 3, and then the square root of 3 plus the square root of 3. I feel like I've done something kind of weird here. Let me make sure. Let's see. I feel like this first term is, let's delete this first term. I feel like that doesn't fit into our sequence here. And the square root of 3 plus the square root of 3 plus the square root of 3, and so on. So here it looks like our next term, a sub n plus 1, is equal to whatever the previous term was added inside the square root of 3 plus that. I've said that probably in the most obsequious way possible. I feel like I really was like, let me just say all the words around this. What it looks like here is I have root 3, and then my next thing is the square root of 3 plus what I had before. And then my next one is the square root of 3 plus what I had before. And so on and so on and so on, which looks like this. I would say typically you're not often asked to like figure out a recursive formula given a list, but that's not to say you couldn't be, right? It's certainly something you could be asked. It just feels like a less typical thing. Let's see. There are other examples I have that I wanted to mention. That's kind of most of them, though. Oh, yeah. So one thing that is interesting, though, about these recursive sequences is their limit's a little bit more interesting to find. And by interesting, I mean challenging. The limit of a recursive sequence is usually more challenging to find. So let's actually look at this example. Yeah, sure. So let's say, so for recursive sequence, you also have to usually be told at least one of the beginning terms. So here, our a sub 1 is, that's what I was thinking, is the square root of 3, and a sub n plus 1 is the square root of 3 plus a sub n. And just to make sure this actually works, right? Our a sub 2 should be the square root of 3 plus a sub 1, which is the square root of 3 plus the square root of 3. And then our a sub 3 should be, again, looking at my formula, a sub 3 should be the square root of 3 plus a sub 2. And then we just, write that in there. It's the square root of 3 plus the square root of 3 plus the square root of 3. So, question. Does this converge? And if it converges, what does it converge to? This is where things get dicey. So how can we decide whether or not this converges? Well, I think it boils down to the monotonic bounded theorem about convergence. So first things first. First things first. What seems like the easier thing to me first, is it bounded? Usually one side of the bounding is always pretty easy. It's definitely always bigger than or equal to zero. Certainly, a sub n is bigger than or equal to zero for all n. Okay, so then you have to make a guess, kind of. And so really, I would say the guess here is going to come from knowing what the limit actually is. So we're going to come back to the upper bound in a second. I promise you there is an upper bound, but you kind of need to know what the limit is to make the argument for what the upper bound is going to be, at least to do it nicely. So we're going to skip that part for now. We're going to come back to it. The other question is it monotonic? So is, well, let's see. First of all, does it look like the second term is bigger than the first term or vice versa? What's bigger? Is A2 bigger or A1 bigger? Yeah. A1, A2 is definitely bigger than A1 for sure. So then we're thinking the subsequent term is bigger than the current term. So really the question is A sub n plus 1 bigger than A sub n? And we can't do what we did last time to show something was monotonic. We can't take a derivative here because we don't have an explicitly defined formula. So we just have to kind of actually do it. So the question is, all right, here's my, where'd you go? Here's my A sub n plus 1. So is the square root of 3 plus A sub n bigger than A sub n? Good question. Well, we're going to try and solve this inequality by isolating A sub n. So let's square both sides, which is totally legit in inequality as long as both sides are positive already, which they are. And then I'm going to bring everything to one side. So I'm going to say 0 is bigger than A sub n squared plus, sorry, minus A sub n minus 3. Ugh, ugh, ugh. Is that true? Well, here's the issue. This doesn't factor very nicely, right? Does that factor? Quadratic formula. So here's the thing. Here's what you think about that. That thing on the right-hand side is quadratic, meaning it's parabola shaped if you graph it. And certainly we would expect this upward opening parabola, the middle of it to be less than zero, right? If there's going to be a part that's below the x-axis, it's the middle part if your parabola opens upwards. So we want to know, are we starting between the intercepts, essentially? So I didn't really intend to use the quadratic formula here, but we're going to do it anyway. So the solutions here would be A sub n is equal to negative b plus or minus the square root of b squared minus 4 times 1 times negative 3 all over 2. So the question is, are we between 1 minus the square root of 13 over 2 and 1 plus the square root of 13 over 2? Well, certainly we're bigger than the negative number. Are we less than this number? Where'd we start? When we started at square root of 3. Is the square root of 3 smaller than 1 plus the square root of 13 over 2? Well, let's see. The square root of 3 is about 1.7. Square root of 13 is for sure bigger than 3. 1 plus 3 is 4. 4 divided by 2 is 2. So this is definitely bigger than the square root of 3. So our first A value certainly starts in the place where this is true. But I'll admit it feels a little like I'm hand waving here. Like I feel a little shaky here. So let's go ahead and do the end part and then we'll come back to this part because the upper bound part is really what's going to be the thing that kind of solidifies things here. So how do we actually try to find this limit? Assuming it exists, which it does, but we're going to show it. So we want to find the limit as n goes to infinity of A sub n. Well, here's some good news. If a limit exists of a sequence, it doesn't matter if you find the limit of the nth term or the n plus 1 term. It's also true that this is equal to the limit as n goes to infinity of a sub n plus 1. So that means the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of the square root of 3 plus a sub n. We're about to see the same thing we just saw before. And again, yeah. I apologize for picking terrible numbers because I thought the numbers were going to work out and my brain was not working the right way. So the numbers are going to be a little bit ugly. Sometimes that's life. So here, if this limit exists, it's equal to some number. So the limit of a sub n is going to be some number L, and the limit of the square root of 3 plus a sub n is going to be the square root of 3 plus L. So squaring both sides, bringing everything to the left. Oh, that looks familiar. It looks like our limit's either going to be 1 plus the square root of 13 over 2 or 1 minus the square root of 13 over 2. Not the 3 I was hoping for. Sorry. So we're going to get L equal to either 1 plus root 13 over 2 or 1 minus root 13 over 2. One of those doesn't make any sense because we know our values start off positive and get larger. Or at least we think they get larger. So this is the upper bound for our sequence. Again, apologies for it not being beautiful and lovely like I meant for it to be, meaning it's not an integer. But here's the idea. Once you know what the limit is, you can say, cool, check this out. We're going to go back to here. I said I'm going to write it down here. So for the upper bound part, we know that a sub 1, which is root 3, is for sure less than 1 plus root 13 over 2. And then here's what we can say. Then the next term, oh, sorry. We can say then if a sub n is less than, I'm just going to call this L, we can show that a sub n plus 1, which is equal to the square root of 3 plus a sub n, is also less than that value. And it might feel like, really, James? You're saying that's true? Well, this is where I'm about to feel like I feel like this is going to get very dicey here. Yeah, I'm a little worried about this, to be perfectly honest. But the idea here is to say that, okay, well, we know that a sub n is less than L. So then if this is less than L, then a sub n plus 1, which is equal to the square root of 3 plus a sub n, is less than the square root of 3 plus L. And we are in the middle of the parabola where this part here is less, is like we essentially have that this inequality here is still, let me double check, is less than 0. So we can say that this is less than L also because 3 plus L is less than L squared. And now I feel like I'm going to say the wrongest thing ever. Sorry, brain. Yeah. Yeah, these numbers. So nice. Sorry, I feel like I've led you astray here. Because what I want to say is what feels very wrong. This is that. Oh, wait. No, yeah, that's what I want to say. I want this to be that, which is that, which should be less than that because it's supposed to not get too big. But then that would mean that, which would mean then, but that feels like the opposite thing of what I said. Well, shoot. I'm sorry. I apologize for leading you down this path of terribleness. Yeah. Let me show you the example that's better. Sorry. Sorry. I feel bad when I'm like, oh yeah, this is gonna work out fine. And then I get lost in my own head. So here's the example I meant to show you, but I thought, oh, I'll just change it up a little bit. That's why you don't do things on the fly. So here's the example I should have been showing you. Here's my actual recursive sequence. Apologies for the inanity. So a sub n plus 1 is the square root of 6 plus a sub 1. And a sub n, sorry. And our first value is the square root of 6. So then our a sub 2 is the square root of 6 plus the square root of 6. Our a sub 3 is the square root of 6 plus the square root of 6 plus the square root of 6. And what you can show here is that this thing is bounded by, well, let me just show you how to do it. Instead of telling you, let me actually do the right work. So if I want to find the limit as n goes to infinity of a sub n, it should be equal to the limit as n goes to infinity of a sub n plus 1, assuming it exists. So then this is going to be the limit as n goes to infinity of a sub n. It's equal to the limit as n goes to infinity of the square root of 6 plus a sub n. We're going to say that this limit is L. The thing I'm doing here, in case you were a little bit dicey how I did before, is we're just doing the limit the usual way. We're passing the limit through and getting 6 plus the limit as n goes to infinity of a sub n. So that's going to be the square root of 6 plus L. And now we end up getting our limit is equal to the square root of 6 plus our limit. We square both sides. We bring everything to one side. You get L squared minus L minus 6 equals 0. You do factor this because it's not stupid numbers that I came up with. And you either get L equal to 3 or L equal to -2. Clearly, -2 is not the limit. So 3, if limit exists, is what the limit is equal to. So here's then what we can do. We can say that, we can say that it looks like well, first of all, our a sub 1 equal to the square root of 6 is definitely less than our limit, which is equal to 3. And then to show that the sequence is bounded, we're going to use what's called an inductive argument, where we're going to say this is true at some point in the sequence. And then we're going to show that if it's true for anything in the sequence, it's true for the next. That's the whole basis of induction, where you say it's true for some base case, and then we're going to prove that if it's true for the nth case, it's true for the n plus 1 case. So then if it's true for n equal to 1, it has to be true for n equal to 2. True for n equal to 2, for 3, for 3, for 4, for 4, for 5. That's what an inductive argument is. You show it's true at some point, and then you show that if it's true for any nth value, it's true for the next one, and then shows it's true for all positive integers. So we're going to show that if our, oh, that's interesting, a sub n is less than 3, then a sub n plus 1 also must be less than 3. So check it out. So we're going to assume a sub n is less than 3. Then, and here's going to be, you're going to be like amazed at how much better this problem is doing it with nice numbers. Check out how nice this is. Then a sub n plus 1, which is equal to the square root of 6 plus a sub n. Well, we know that a sub n is less than 3. So this is less than the square root of 6 plus 3, which, oh my God, look at that. It's 3. That's why you use good numbers, not terrible numbers. Oh, look, we did it. We showed that if a sub n is less than 3, then the next term also is less than 3. So then we know that a sub 1 is less than 3, which implies a sub 2 is less than 3, which implies a sub 3 is less than 3, and this goes on forever and ever and ever. Which means a sub n is less than 3 for all n. Or in other words, the sequence a sub n is bounded. That's how you show it's bounded. By knowing what the limit already is. But you can't prove the limit exists without the theorem, right? You can say, well, if the limit exists, then it's going to be this. But then you actually have to say, well, the limit has to exist because the sequence is bounded and monotone. I know it kind of feels very circular, like we're going back, but that's kind of what's happening. Yes, probably, yes. So, sorry, paper speed. All right. So that's most of what I want to say about sequences. Not that there isn't more to, well, in fact, that's not true. Because really everything we're about to talk about is also sequences, right? Every series is a sequence. So we'll talk about some series. And I know I wrote down some examples here that I wanted to make sure I got to. Where'd you go? Examples over there we are. Yeah. Oh, yeah. Let's look at that one. So let's say, so first of all, series is just a sum of terms in a sequence. And we are often concerned with whether or not a series is convergent or divergent. That's usually what we're getting at towards, even if we haven't quite started there. Let me see one thing here. So let's look at some examples. Let's say we have the sum from n equals 1 to infinity of n plus 3 over 2n plus 1. We start writing out some terms. So I've got, let's see, 4 over 3. I hate writing out terms. It just feels like the big, I mean, I know it's like sometimes useful, but most of the time for this, it's not that useful. 5 over 5, 6 over 7, 7 over 9, and so on and so on and so on. So the question we want to answer here is, does this series converge or diverge? And there's going to be many, many, many tests for convergence and divergence. One of them, which is so, like in 21B, when you were doing integration, and kind of like when you looked at the integral, if it wasn't immediately easy, you usually would say, well, let's try a U sub. At least that's what I would have said you should do. It's like if you look at something, you're not sure what to do, try U substitution. Pick a U, see if its derivative shows up, see if you can integrate it. In the same sort of way, when you're trying to see if a series is convergent or divergent, the first thing you should always check is what's called the nth term test, or the test for divergence. I want to point out this test, so named, will only ever show you that a sequence diverges, or it won't tell you anything. It will never tell you a sequence. Sorry, I apologize in advance already. I'm going to make that mistake too many times. I'm going to say sequence when I mean series, or I'm going to say series when I mean sequence. So let me back it up. The test for divergence, the nth term test, the same thing, can only show you that a series diverges, or we don't know anything. Or as we like to say, it either diverges or it might converge. So in this case, here's what we do. We ask ourselves, what is the limit as n goes to infinity of the sequence that we're taking the series of n plus 3 over 2n plus 1? What's the limit of that? Well, it's 1/2. Or we have the usual rational function kind of thing where it's 1 times n to the first over 2 times n to the first. So what this means is the terms of my sequence are getting really, really, really close to 1/2. So if we think about this here, what we're doing here is we're adding out essentially 1/2 plus essentially 1/2. And we're doing that forever. What's 1/2 plus 1/2 plus 1/2 forever? a lot. It's infinitely large. If you add up what half of infinity, still infinity. If you add up a non-zero thing or something that's not getting close to zero an infinite number of times, you're going to get infinity. So this series diverges. The sum from n equals 1 to infinity of n plus 3 over 2n plus 1 diverges. And the reason is because the sequence has a limit that is not zero. If your limit of your sequence is not zero, that means you're adding up something that is not zero an infinite number of times. And that's going to give you infinity. So there's two names for this. This is called the nth term test because you're literally testing the nth term. It's also called the test for divergence because it only can tell you that a series diverges. So the way it's typically phrased is if the limit as n goes to infinity of the sequence is not zero, then the series diverges. And just to tack on here, an addendum, if the limit as n goes to infinity of a sub n is equal to zero, then anything can happen. The series could diverge, the series could converge. But really what that means is you have to use a different test. So if you ever hear yourself saying the words, the series converges by the test for divergence, think again, right? You can't converge by the test for only testing divergence. So here are kind of some, let's see, where do I want to go next here? Just want to see one thing. Yeah, yeah. So, yeah. So for example, this series from n equals 1 to infinity of 1 over n, if we look at the limit as n goes to infinity of 1 over n, that's going to be 0. We don't know anything. We don't know yet if this series converges or diverges. I will tell you it diverges without any justification yet. On the other hand, this series from n equals 1 to infinity of 1 over n squared, the limit of the sequence is also 0. And we also don't know anything yet. But I'll tell you this one converges. So the whole point here is that if the limit is 0 of your sequence, the series could converge, the series could diverge. And you have to do something else to make that determination. But I'm getting a little ahead of myself, I feel like. So I'll just point out a couple more examples. This series from n equals 1 to infinity of 1 minus 1 over n to the nth power, definitely, well, let's check. We look at the limit as n goes to infinity of 1 minus 1 over n to the nth power. Could that limit ever be 0? You have something that's getting really close to 1 and a power that's very, very large. No. In fact, we should all know what this is. It's almost E. It would be E if it was 1 plus 1 over n to the n. But really, we have the limit as n goes to infinity of 1 plus negative 1 over n to the n, meaning the limit's going to be e to the negative 1. Still not 0. So since that's not 0, we can say that this series diverges. Here's another good one. I would ask this on the test. The sum from n equals 1 to infinity of cosine of 1 over n. I'm going to say again, reemphasize here. Whenever you have a series and you're asked about its convergence or divergence, you don't even have to write it down, but you should at least ask yourself, okay, what's the limit of the sequence? Is it zero? Cool, I'll move on. Is it not zero? Great, I'm done. That series diverges. That's the case here, right? The limit as n goes to infinity of cosine of 1 over n is going to equal cosine of 0, which is 1. So this series also diverges. So I would encourage you to get in the automatic habit of if you're asked about a series being convergent or divergent, double check that the sequence has a limit that is equal to 0. Because if it's not 0, you have finished. The series diverges. Yeah. Time. There's never enough time. That's what happens when you spend 10 minutes doing the wrong problem. Sorry about that again. I really do. Didn't mean for that to go so poorly. What I'll say is we should next time really talk about this finding the sequence of partial sums. I would say kind of. I don't think you do a whole lot of that in actuality, but there's a couple examples that you should be aware of. For example, something like the sum from n equals 1 to infinity of 2 over n minus 2 over n plus 1, which might be written as the sum from n equals 1 to infinity of 2 over n squared plus n. Written like this, it's kind of hard to see what's going to happen. In fact, if you have something like this, maybe bad news if you didn't like partial fractions, you can do a partial fraction decomposition to write this like that. Yeah, partial fractions are still a thing that we sometimes encounter. But if we start writing out terms here, look what happens. We get this sum from n equals 1 to infinity of 2 over n minus 2 over n plus 1 is equal to 2 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus 2 over 3 minus 2 over 4 plus 2 over 4 minus 2 over 5. And lots of things cancel. In fact, almost everything cancels. This cancels with that. This cancels with that. This cancels with that. This cancels with that. So it looks like it's going to end up being just 2. But to be more precise, we should do something else, slightly different. We should find the formula for the sequence of partial sums. So I'll point out my first partial sum is just my first term, which is 2 minus 2 over 2, which is just 1. I don't really care what it's equal to. My second partial sum is 2 minus 2 over 2 plus 2 over 2 minus 2 over 3. I really shouldn't write all that out. I know it's just going to be 2 minus 2 over 3. My third partial sum is going to be 2 minus 2 over 4. And I feel like I could probably write a pattern at this point. Let's see, one more. My fourth partial sum is going to be 2 minus 2 over 5. What do you think my fifth partial sum is going to be? Yeah. Okay, harder question. What do you think my 100th partial sum is going to be? 2 minus. Cool. So then I bet you could all tell me that my nth partial sum is going to be 2 minus 2 over, right, n plus 1. Which totally makes sense, right? If you actually write out the terms, right? If you actually write out Sn, and this is going to be kind of unwieldy. It's 2 minus 2 over 2 plus 2 over 2 minus 2 over 3 plus all the way out to the nth term, which is going to be 2 over n minus 2 over n plus 1. Oh yeah, that cancels that, that cancels that, that can't cancel, and that cancels that, and you're left with exactly 2 minus 2 over n plus 1. And then we can say that the limit as n goes to infinity of our Sn is the limit as n goes to infinity of 2 minus 2 over n plus 1, which is equal to 2 minus 0, which is 2. So that means the series converges to 2 because the sequence of partial sums converges to 2. So the way we would really write this is just the sum from n equals 1 to infinity of 2 over n minus 2 over n plus 1 equals 2. But again, I want to emphasize here that this really means that we know that the series converges, which means the sequence of partial sums converges, and it converges to the value of 2. That is all the things you were saying when you say that the series is equal to a number. I won't do this one, but I'll point out that you on your own should try to justify to yourself why the sum from n equals 1 to infinity of the natural log of n plus 1 minus the natural log of n is also a telescoping sum like this, but that one's going to diverge. We'll talk about it on Friday.